Let's start with the main body of our training course. And just to help you position where we start from, we are in the improve phase of the make. Second module, multiple regression analysis, and we're going to talk about data transformation, Box-Cox. Before I continue, let me give you a little bit of perspective. You may remember that the normal distribution in statistics and in Lean Six Sigma is the most widely used and most useful distribution that we have come across. And this is due to the symmetrical shape of the distribution, where its half mirrors the other half. So symmetry is key. And we call it normal distribution, which means that the data is normally distributed around the mean, and the empirical rule in statistics is applicable. Now, normality is a very important assumption for many statistical tests and techniques. This assumption overleads to tests that are simple, mathematically sound, and powerful compared to tests that do not make the normality assumption. A Box-Cox transformation is transforming non-normal dependent variables into a normal shape, just like the figure that we have on our slide. So on the left-hand side, you can see the distribution of temperature measured in degrees Celsius, centigrade, and on the right-hand side, temperature in degrees Fahrenheit. So this is an example of where this data transformation can be applied. Normality assumptions are critical for many univariate intervals and many hypothesis tests. So it is important to test and validate this assumption before conducting a statistical test. You may remember that we have different ways to test for normality. I had mentioned the Anderson-Darling normality test, which is a test using statistical process control. We can also use the visual inspection to see if the shape of a distribution is approximately normal, or we can use a visual inspection of a histogram, a probability frequency distribution. If the data are not normal, the Box-Cox normality plot can often be used in order to find a transformation that will approximate normality in the data. Just like in the figure. Box-Cox normality plots are formed by, on the horizontal axis, the value of lambda, and on the vertical axis, we have correlation coefficient from the normal probability plot after we have applied the Box-Cox data transformation. So many statistical tests and intervals are based on the assumption of normality. Unfortunately, in the real world, many real data sets do not follow the normal distribution. In fact, they're not approximately normally distributed. However, an appropriate transformation of a data set can often yield a data set that does follow approximately the normal distribution. This increases the applicability and usefulness of statistical techniques based on the normality assumption. So, the Box-Cox data transformation is particularly useful family of transformations. This means there's not one unique particular transformation. It is a family. Just like normal distribution, except from the standard normal distribution, we're always referring to a family of normal distributions that they have most likely different means and different standard deviation. It is defined by the formula that is illustrated on our slide, where the y is the response variable, which is the dependent variable, the output, and lambda is the transformation parameter. For a value of lambda that is equal 0, natural log of the data is taken instead of using the above formula. Given a particular transformation, such as the Box-Cox, it is useful to define a measure of normality of the resulting transformation. One such measure is the correlation coefficient of a normal probability plot. So the correlation is computed between the vertical and the horizontal axis variables of the probability plot, and it is a convenient measure of the linearity of the probability plot. The more linear the probability plot, the better a normal distribution fits the data set. This plot of correlation coefficients applies for various values of the lambda parameter. So the value of lambda corresponding to the maximum correlation of the plot is then the optimal choice for lambda. The histogram of the upper left-hand corner shows a data set, first column, that has significant right skewness. However, because of the skewness, it does not follow a normal distribution. So, in these examples, we can see the transformation from a non-normal distribution into a data set that approximates normality. Box-Cox normality plots are not a standard part of most general-purpose statistical software programs. However, the underlying techniques are based on a normal probability plot and computing a correlation coefficient, which is doable for most statistical software packages. So, if a statistical program supports these capabilities, writing a macro for a Box-Cox normality plot should be feasible. For example, you can use Minitab in order to perform a Box-Cox transformation, and the figure that we have posted on the slide is an example of a Minitab report for this type of transformation.